control system. So let's see what is the problem. So our problem is, we are given the open loop transfer function of a control system, that is Gs equals to K upon S, S plus 6 and S square plus 4S plus 30. And we have to sketch the root locus of this system, and we have to determine the breakaway point, the angle of departure from the complex poles and the stability condition. So let's try to solve this problem. Our first step will be to find out the poles and zeros of this system. So step 1 will be to find out the poles and zeros. Poles will be obtained by equating the denominator terms to 0. So first we will have S equals to 0. Then our second pole will be S plus 6 equals to 0. That is S equals to minus 6. And our third pole will be S square plus 4S plus 13 equals to 0. So when we solve this quadratic equation, its root will be minus 2 plus J3, and the second root will be minus 2 minus J3. So we are having 1, 2, 3, 4 poles. And for zeros, we have to equate the numerator to 0. We are having no terms here of S. So we are having no 0 for this system. 4 poles and no 0. Now our second step is to find out the asymptotes. For asymptotes, first we will find out the intersection point of the asymptotes with the real axis. So for this we have the formula x equals to summation of poles minus summation of zeros upon P minus Z. So it will be poles we are having S equals to 0, S equals to minus 6. So we will find out the sum of all these minus 6. We have minus 2 plus J3 and we have minus 2 minus J3. So this is the sum of the poles. Now zeros we don't have any 0 here, so we will put 0. Then P minus Z, we are having 1, 2, 3, 4 poles and this is 0, so 4 minus 0. Then we will have minus 6 minus 2 plus J3 minus J3, they will be cancelled out. So we will be having minus 6 minus 2 that is minus 10 upon 4. So x will be equals to minus 2.5. So this is the intersection point of asymptotes with the real axis. Now we will find out the angle of asymptotes. To find out the angle, we are having the formula theta equals to 2m plus 1 into 180 degree upon P minus Z. it ranges from 0, 1 till it is t minus z minus 1. We are having 4 poles and we are having no zeros. So 4 minus 0 minus 1, that is 4 minus 1. So we will be having 3. That is m will be equals to 0, 1, 2 and 3. Okay. Now putting the values of m here and we will find out the value of theta. So theta will be equals to, first putting m equals to 0. So we will have 2 into m, that is 0, plus 1 into 180 upon p minus z, that is p is 4. So we will have 4 here. So theta will be equals to 2 into 0, 0, 180 by 4. So it will be theta equals to 45 degrees. Now m equals to 1, theta equals to 2 into 1 plus 1 into 180 degrees upon 4. Okay. So here we will get the value of theta as 135 degrees. Now m equals to 2, theta equals to 2 into 2 plus 1 into 180 degrees upon 4. So here theta will be equals to 225 degrees. For n equals to 3, we will have theta equals to 2 into 3 plus 1 into 180 degrees upon 4. So here theta will be equals to 315 degrees. So we have got 4 values of theta. For n equals to 0, we have 45, then 135, then 225 degrees, and then 315 degrees. So these are the 4 asymptotes, okay, and these are the angles of the asymptotes. Now we will find out the breakaway point. So our next step, that is step number 3, will be to find out the breakaway point. So to find out the breakaway point, we will differentiate the open loop transfer function with respect to s and then equate this differentiation to 0. Okay. So differentiation of gs is given to us as k upon s plus 6 and s squared plus 4s plus 30. So differentiated with respect to s, dgs by ds will be equal to, we are having this as minus k, then s plus 6, s square, because differentiation of s will be 1, then remaining terms as it is. Then we have plus s, differentiation of s plus 6 will be 1. So it will, remaining terms we will write them as it is. Then we have s plus 6 and differentiation of s squared plus 4s plus 13 will be 2s plus 4. Okay. So this is the differentiation of the open loop transfer function. Now if we equate this to 0, we have to equate it to 0. So we will open this, we will have minus k. This is s to the power q plus 4s square plus 13s plus 6s square. Then we have to multiply this inside. We have s square plus 4s square plus 13s plus we have to multiply these 3 terms. So we will be having s square plus 6s and then 2s plus 4. And we have to equate it to 0. Okay. Now when we solve this, we will have minus k, then 4s cube plus 30s cube plus 74s is equals to 0. So we are having 4s cube plus 30s square plus 74s plus 78 equals to 0. So this equation we have obtained after simplifying this. Now if we find out the roots of this equation, then we will find the value of s is equals to minus 4.2. So this s equals to minus 4.2, it is the breakaway point. Okay. Now we have obtained the breakaway point. Now our next step will be step number 4. We will find the intersection of the root locus with the imaginary axis. Now to find out this intersection of the root locus with the imaginary axis, we have to first find out the characteristic equation of this system. So characteristic equation is given by it is 1 plus gs hs equals to 0. Gs is given to us in the question and hs, because it is a unity feedback system, so hs will be equals to 1. We will find out 1 plus gs hs, that is k upon s, s plus 6, and then we have s square plus 4s plus 13 equals to 0. So when we solve this, we will find out the characteristic equation as s to the power 4 plus 10s cube plus 37s square plus 78s k equals to 0. So this is the characteristic equation of this system. You have to just multiply this and find out the equation. You will get this equation. Now for finding the intersection of the root locus, we will use Roots-Hurwitz criteria. Okay. And Roots-Hurwitz criteria, for this we will have to form the roots array using this characteristic equation. So let's form the roots array. The highest power of s in this equation is s to the power 4. So we will start from s to the power 4, then s cube, s square, s to the power 1, and s to the power 0. Coefficient of s to the power 4 is 1, s square is 37 square, and then s to the power 0 is k. So here we will be having 1, 37, and k. The coefficient of s to the power cube is 10, and then 78 coefficient of s to the power 1. So we will be having here 10, 78 and 0. Find out the coefficient of s square, multiply this with this, then 1 minus this into this upon 10, that is 10 into 37 minus 78 into 1 divided by 10. So when you solve this, you will get the value as 29.2. For this, we have to multiply 10 with k, then multiply 1 into 0, that is 0, and divide by 10. So you will get the coefficient here as k only. This will be 0. Now for s to the power 1, you have to multiply this into this, then multiply this into k, and divide by this term. So we will get the coefficient as 78 minus 0.34 k, and it will be 0. Now for s to the power 0, you have to multiply this with this into this, divide by this, get here k only, and this is 0, 0. So we have formed the roots array using the characteristic equation of the system. Now for stability, or we can say that finding out the intersection point with the imaginary axis, we have to put these coefficients which are having the k term equals to 0. So 78 minus 0.34 k equals to 0. So 78 equals to 2.k. So k will be equals to 78 divided by 0.34 and its value is 29.4. Okay. This is the value of k which we have obtained from the rules array. Now we will find the subsidiary equation using the coefficients just above this and we will form the subsidiary of the auxiliary equation. Auxiliary equation will be 29.2 s square. So next we will form the subsidiary or the auxiliary equation and we are having this as 29.2 s square plus k equals to 0. K we have already obtained its value as 229.4. So substitute its value in this equation. We will get 29.2 s square plus 229.4 equals to 0. So from this equation, obtain the value of s. So s square will be minus 229.4 divided by 29.2. So s will be equals to plus minus 2.8 j. Okay. This is the value of s. So we are having the two intersection points of the root locus with the imaginary axis. One is plus 2.8j and second is minus 2.8j. Now next we have to obtain, this was our step number 4. Now step number 5 is to find out the angle of departure from the complex poles. Because always we find out the angle of departure when we are having complex poles of the system. Okay. So for this we have the formula phi d, that is the angle of departure. It is equals to 180 degree minus phi p minus phi z. What is phi p and phi z? This is the sum of the angles subtended by all the other poles on this pole, complex pole. Okay. So phi p, it is what? Sum of all the angles subtended by remaining poles. And phi z is what? Sum of all angles subtended by zeros. Okay. Now here we have to find out the angle of departure from the complex pole. So you have to keep a note here in your mind that notice the angle of departure is tangent to the root locus at the complex pole. Okay. So for complex pole, the angle of departure, it is what? It is tangent to the root locus. So our formula for phi p1, when we want to find the angle subtended by the remaining poles, so phi p1, it will be 180 degree minus, we have tan inverse of, because we are having the complex pole as minus 2 plus 3j, we are having minus 2 plus 3j and minus 2 minus 3j. So our phi p1 will be 180 degree minus tan inverse of 3 by 2. And phi p2, it will be tan inverse of 3 by 4. its value will come out to be 123.6 degrees, and the value for this will come out to be 36.86 degrees. Because we are having 4 poles, so we are here we are calculating the angle of departure for one complex pole. So we will obtain phi p1, phi p2, and phi p3. Phi p3 will be 90 degrees, because one complex pole, it will subtend an angle 90 degree on the other complex pole. This you can obtain, these angles you can obtain by applying the trigonometric identities on the root locus. Then you can easily find out these angles. And then we have the angle phi z. Okay, because phi z, we are having no zeros in this, so phi z will be 0. So this phi d, that is the angle of departure, it will come out to be 180 degree minus phi p minus phi z. So phi d will be 180 degrees minus, we have first angle as 123.6 degrees, then plus 36.86 degrees, and then 90 degrees. These are the 3 angles. Now phi d, it will be 180 degrees minus this sum, that is 123 plus 36.86 plus 90 degree. Okay. Sum of phi p. Then phi d, it will come out to be minus 70.46 degrees. So this is the angle of departure. So our question was to sketch the root locus, and also we have to find out the breakaway point, the angle of departure from the complex pole, and the stability condition. We have obtained breakaway point, angle of departure, and the stability condition. All we have obtained. Now let's sketch the root locus of this system. We are having 4 poles. Okay. First was s equals to 0, then second was s equals to minus 6. So we are having s equals to minus 6 here. Then we have s equals to 0 here as a pole. And then we have 2 complex pole, minus 2 plus 3j, minus 2 minus 3j. So minus 2 will be somewhat here. This is minus 1, minus 2. So minus 2. This is plus 3j. This is minus. This is j. This is minus 2j. This is minus 3j. Similarly here, j, 2j, then 3j. So this is s equals to minus 2. And here we are having the pole minus 2 plus 3j, and here we are having a pole s equals to minus 2 minus 3j. Zeros, we don't have any zero in this system, so we are not going to plot in this. This was our imaginary axis. And this is real axis. Now we have to obtain the direction of the root locus. So if we take for this pole here, take a point, the number of poles and zeros on the right hand side of this point, that is 1, 2, 3, 4. 1, 2, 3, 4. We are having 4 poles. So it is an even number. So the direction of root locus will be towards the origin. It will be like this. Okay. Now for this pole, if we take, the number of poles and zeros will be 1 on the right hand side. So the direction of root locus will be towards this point. Okay. So it will go towards this. It's somewhat like we go in this direction, and it is k equals to infinity. here we are having k equals to 0. Starting from a pole and it has to terminate at a 0, but it will not terminate at 0, it will go to infinity. So it will start from here, it will come to this point and it will go towards infinity. Similarly, here also it is going to diverge and it will go towards infinity. Because it is starting from a pole and terminating at 0, here we are not having 0, so it will terminate at k equals to infinity. This will also start from this 0, that start from this pole k equals to 0 we are having here, and it will terminate at k equals to infinity. Similarly here, starting from k equals to 0 and terminating at k equals to infinity. Okay. Now for all these three, so for these three branches, okay, we are having 1, 2, 3, 4. Sorry, 4 branches. So for these 4 branches, we are having asymptotes. Its direction is like this, and its direction is like this. We are having asymptotes, so we will draw these asymptotes here. These asymptotes are making the angle. This asymptote will make an angle 135 degrees. This will make an angle 45 degrees. This will make an angle 225 degrees. And this asymptote, it's going to make an angle 350 degrees. Because we were having three values of theta: 45, 135, 225, and 350. So these are the 4 asymptotes. One for this, second for this branch, third for this branch, and fourth for this branch. So all these angles they are making, and we are having this as the breakaway point, that is s equals to -2, and we are having one branch of root locus which is starting from this pole s equals to 0. Because for this pole, if we take a point here, then number of poles and zeros on the right hand side is 1, that is odd. So the direction of root locus will be here. So for this pole, we are having two branches of the root locus, so they will break at this point. Now breakaway point, we were having -4.2, so this is s equals to -4.2. That is the breakaway point where the branches of these they are coinciding and then they are going towards k equals to infinity. So this is the complete root locus of this system. We have plotted all the branches of the root locus here. We have plotted the angles also, and then the breakaway point also. We have mentioned all the things on this root locus. So I hope this problem is clear to you. Thank you.